Hi everyone, and welcome back to our discussion of synchrotron radiation, where we are in the middle of learning about the radiation spectrum from a power law distribution of particles. So as a reminder, we looked at the radiation spectrum from a single particle, and then we started looking at what might happen if instead of a single particle, which is of course never the case in astrophysics, you have a distribution of particles. We made an assumption or took a specific case for a particular distribution of particles. Here it's a power law distribution in energy. And then we said, let's look at that power law distribution. Let's assume that our particles are distributed like that in energy. And let's see what the radiation is that we get out of that. We did this a couple of ways. We first looked at the intuitive approach, where we just said, well, let's just look at how much radiation the particles produce at each frequency. And we assume that each particle produces radiation only at its corresponding characteristic frequency, gamma squared times this omega naught. Using this sort of delta function approximation. And we showed that as a result, what you get out in the spectrum also looks like a power law in that frequency range corresponding to in between the characteristic frequencies of these two Lorentz vectors. And then we said, well, let's do this a little more rigorously mathematically. And so we wrote down an expression where we take the synchrotron spectrum from a single particle, which is that synchrotron F function, and we convolve it. We convolve the emissivity of a single particle with the distribution of particles. And then that spits out this expression, this integral here. And then we are looking at the different regimes of that integration. There are three different regimes that we wrote down. These correspond to different behaviors of this of the integrand of the synchrotron F function. I kind of very briefly sketched out what this might look like when both of these integration limits are much larger than 1, and that's when you are in a part of frequency space that corresponds to radiation from above this this omega 2 corresponding to this gamma 2, and then you get an exponential cutoff. And then we did this case 2, in a fair bit of detail, where we actually looked at this integral. We took the limits from 0 to infinity, and we showed that it basically kind of spits out a bunch of gamma functions. And then we also integrated over the particle velocity angle distribution, so over alpha. And that alpha, just remember, is the pitch angle between the particle's velocity vector and the magnetic field. And then that spits out another bunch of gamma functions. And so really we get a bunch of p-dependent corrections to the normalization of the emissivity. But the important thing to keep in mind is that the emissivity still depends upon the frequency to this power law, 1 minus p over 2. And this connection between this power law index here, 1 minus p over 2, and this index here, p, is the most important thing that we should get out of this aspect of this analysis. And then finally, I left this last example, or the last case, as an exercise for you, where we said, what happens when x max is much less than 1, and that'll push x min also to be much less than 1, because x min is by definition less than x max. And I said, what the result that you'll get if you do that mathematically by putting those regions into those regions of validity into those limits of the integration, you will find that your integration just gives this whole thing turns into an omega to the 1/3 power. And so in the rest of this analysis and the rest of this video, I'm going to do that integration for you so you can check your results. And then at the end of this video, we're going to put all of that together, and we're going to look at what the synchrotron emission spectrum looks like for a power law distribution of particles. And you'll see that there's various kind of breaks in it. And that's in the absence of additional effects like propagation effects, synchrotron self-absorption, synchrotron cooling, and those are aspects that we'll talk about after this. And so if you've already done all of that calculation, if you've taken this limit and you put it in there and you found that it's proportional to omega to the 1/3, then feel free to skip to the end of this video where we start putting this power law distribution together with all of these regimes, and we have the final expression. The final kind of plot of what the spectrum looks like, because there we are going to be talking a little bit about how we can intuitively understand where the different power law segments come from, and we'll connect that with the mathematics and with some of the physical insights we had earlier. And if you'd like to just check whether your mathematics follows along with what we have here, then feel free to watch between now and that point as well. So in this video, we're going to talk about this regime, and then we're going to put all these regimes together and have the final synchrotron spectrum in the absence of cooling and self-absorption, which will be the topic of subsequent videos. All right, so let's have a look at this, this regime of x max and x min both much less than 1. So in this regime, we have x min, this is case 3, so our x min is much less than 1, and our x max is also much less than 1. And in this particular case, we can still take our x min, so we can take x min goes to 0. Right? Because it's much less than 1, we can still take it to go to the lower bound of our integral to go to 0. But we can no longer take x max to go to infinity, of course. It's much less than 1, so we can't do that. But now, what are the values that x can take inside the integral? Think about that for a second. What are the possible values of x? And so note that inside the integral, your x is always less than 1. That it must be much less than 1 because the upper bound of the integral is much less than 1. So the values of x inside the integral is much less than 1, which means that you can expand that f of x in the regime where x is much less than 1. And so I've previously given you a sort of an expression for what that looks like, and that's that x to the 1/3. Let me give you the full expression. So that f of x in that regime is approximately given by 4 pi over root 3 gamma to the gamma 1/3. Again, this is the gamma function, not a Lorentz factor. X over 2 to the 1/3 power. And critically, of course, is proportional to x to the 1/3, which is what we had there. And remember, for small values of x, e to the minus x is just 1, and so these make sense. And this is a twiddle. I haven't given you the normalization. This stuff out here is a full normalization. So now we can just substitute this in there because this is for, to be absolutely clear, this is for x much less than 1. Okay, so let's put this in here into our expression for j sin of omega. So here's what that will look like then. So our j sin of omega is going to be proportional to, and so I'm not going to carry all of these various factors of gamma and 4 pi and things like that, and I'm also going to not carry around all of these terms, because what is most important to us is the frequency dependence. And if you want, you can keep track of all of these factors and you'll get the actual full normalization. But let's just look at what the spectral index, the power law slope is. And again, spoiler alert, that's going to be 1/3. So I'm just going to keep track of the frequency bits. So the frequency bit here from the prefactor of the integral is just this omega to the 1 minus p over 2, of course. And then we have this integrand, this bit, or this integral. And that integral, we said we're going to take x min to 0, so that's 0, to x max, which is going to be some value, x max, of f of x, which I'm going to put that in just a second, times x to the p minus 3 over 2 dx. Right, so I've just written that out here, and I've set x min to 0, and I've kept the value of x max, which is much less than 1. And now we can expand this x max. So inside this integral, we have the integral from 0 to x max f of x times x to the p minus 3 over 2 dx. And so this is going to be proportional to, so what are the x bits? It's of course proportional to the 1/3, so we can put that in here. So that's the x dependence. So it's x to the 1/3, x to the p minus 3 over 2 dx. And now we can collect the powers of x, and so that is proportional to the integral. Always put limits from 0 to x max of, I will let you collect these terms, these power law indices, and when you do that, you will get, we have x to the power of 3p minus 7 over 6. And that's just a sum. And so now you can integrate this. So that is going to be proportional, so dx. And now we can do this integral, and so this gives us x to the power of 3p minus 1 over 6 from 0 to x max. Okay? And then this is going to be equal to x max to the power of 3p minus 1 over 6. And of course, now this only works if when x goes to 0, this thing goes to 0. Right? Because if x goes to 0 and this thing does not go to 0, and if it blows up, then you have a problem. And so you will note that that requires this power of 3p minus 1 over 6 to be greater than 1. Right? So if this power law is greater than 0. If this power law is less than 0, then this goes up as you get to smaller and smaller values of p. Smaller and smaller values of x, and you can no longer remove the second boundary term, the other boundary term. And so, as an aside, and I'll put that into different colors, you can keep in mind that that's an aside. This is only valid for p greater than 1/3. Because if p is not greater than 1/3, then this thing becomes negative, and this boundary term will blow up. And so this is an additional, all of this 1/3 thing that we're going to get out depends upon p being greater than 1/3. And when we get to incorporating this into the full spectrum, we'll see why intuitively this makes sense, that p needs to be steep, or this distribution needs to be steep, and steeper than, in this case, this particular value of 1/3. Okay, so now what is x max? So remember, x max is omega over gamma 2 squared omega naught. And so what are we doing here? We're interested in the frequency dependence of all of this. So there's the only frequency part in x max is, of course, the omega. So that tells us that this is proportional to omega to the power of 3p minus 1 over 6, which I'm going to write as p over 2 minus 1 over 6. Right, I'm just breaking this up. And then our j sin of omega, which is over here. So our j sin of omega is proportional to, so there's an omega to the 1 minus p over 2, or actually, just for fun, let me write this as omega to the power of 1 over 2 minus p over 2 times this thing we just got from the integral, omega to the p over 2 minus 1 over 6. And now, behold, the minus p over 2 and plus p over 2 cancel, and we are left with this being proportional to, can you still see it if I write down there? Maybe not so well, so let me put it up here. This is proportional to omega half minus 1/6, which is omega to the 1/3. And so there we have our power of 1/3. And so here our j sin of omega is proportional to omega to the 1/3. It is independent of p in this particular regime. It's just a constant 1/3. Okay, so if you made it this far through the mathematics, congratulations. It's simply a question of taking the f of x and putting in the corresponding power law regime, and then going through this expression and keeping in mind, or keeping track of the bits that matter, which is the proportionality as a function of omega. So just as an aside at this point, when we are doing this sort of integrals and we are like trying to get physical insight from it, it's important to keep in mind what is it that we are most interested in. Like, are we interested in the alpha dependence? Are we interested in the magnetic field dependence? Are we interested in this case, the frequency dependence? And so in this case, it turns out we're interested in keeping track of all the omegas, which is the observing frequency. So that's why this proportionality, right, there's constants of proportionality out front. We can not worry about those. There's magnetic fields in here. So we are keeping track of the omegas, and that's why we ended up with this. If you want to keep track of the magnetic field, and you want to do this quickly and you just are interested in the magnetic field dependence, then you should keep those in mind. And of course, if you want to do this in its full glory, you should keep all of the constants out in the front. But this is a quick way to get out the physical insight that you want by keeping track of those relevant bits of those relevant quantities in your expression. All right, so now we've done case 3, and we've done case 2 in detail, and I've kind of sketched case 1 for you. And so let us put all of this together and try to understand what is going on. So what are we doing? We are convolving the single particle spectrum, which is this. So this is a convolution. We're convolving a single particle spectrum, which is this synchrotron f function. Let me write that as f of omega over omega c. You can also write this as p sin of gamma, if you like, as a function of omega over omega c. And it has this x to the 1/3 e to the minus, sorry, that is brain and hands cross there. This is x to the 1/3 e to the minus x. And it peaks at about 1, or 0.29 if you're being fastidious. And so this is a single particle spectrum which we're convolving with this distribution of particles, or vice versa. You're convolving this distribution of particles with a single particle emission spectrum. And when you do that, what we are actually looking at is, so I'm going to draw some axes. The final J sin of omega, which is the final radiation spectrum that we're getting out of this as a function of the observing frequency omega. Omega. And what is a convolution, right? So a convolution is where you take this thing and you make copies of it with an amplitude that depends upon the other thing. So in this case, we're taking this thing and we are multiplying it here, then we're adding it to more of it as you go to lower and lower Lorentz factors, and it's just larger amounts of this, and then you just keep adding it up until you run out of the thing that you're integrating over in both cases, both edges. And so effectively what we're doing is we are integrating a bunch of these spectra. So we have an omega to the 1/3 e to the minus x, and then another omega to the 1/3 e to the minus x. But as you go to lower and lower omega, there is more and more flux because there are more electrons that make that, that contribute that bump, right? So there's more electrons at lower Lorentz factors. And so it turns out, this is the turns out part, that when you add up all of this, you get a power law here. And the slope of this power law is omega to the 1 minus p over 2. And so then you can see what happens at the edges. So at the very edge where you have the lowest Lorentz factor, so where you have these gamma 1 electrons that are radiating at omega 1, there is no radiation from, so the radiation at frequencies below omega 1 is dominated by the electrons at gamma 1. And so the radiation from them has this omega to the 1/3 tail. Why? Because that's the omega to the 1/3 from these, from this f of x function. So in other words, here we are seeing the radiation from the lowest energy electrons that are radiating at gamma 1, and they're mostly radiating at omega 1, and then down here you're seeing the low frequency tail of that. Why do you not see radiation from the higher energy electrons? You do, but what happens is that there's more of these gamma 1 electrons than there are of electrons at higher Lorentz factors. And this is where this comes in. Because keep in mind that if your P was shallower than this, right, so currently we require P to be steeper than 1/3. If P was shallower than this, then actually there are now enough electrons out at this higher higher Lorentz factors, the contribution of which at those low frequencies does become important, and you can no longer take these limits, and so this falls apart. And so that is why, for steep enough distribution of electrons, the radiation spectrum, the radiation at the lowest frequencies below this corresponding omega 1 is going to be dominated by the electrons that are radiating at omega 1, or which have the characteristic frequency as omega 1. And you can ignore the radiation from the higher energy particles over here that do produce radiation, but it's less, much less, negligible compared to the radiation from the gamma 1 electrons. So that's this end. Other end, also straightforward. Each of these spectra falls off exponentially, and so as you go to higher and higher Lorentz factors here, corresponding to higher and higher critical frequencies here, the only contribution you really get is from the electrons that are radiating at that critical frequency. Because if you're somewhere, if you're like at this edge, then all of at lower frequencies, you have this exponential cutoff from the lower energy electrons. And so that's what gives you the power law. That's case 2. And then the very edge, let's say over here, where you're at omega 2. Beyond this, all of the radiation that you get is radiation from the gamma 2 electrons, and that basically falls off exponentially. So you have e to the minus omega over omega 2, let's say. So the radiation spectrum from a power law distribution of particles, in the absence of self-absorption, in the absence of synchrotron cooling, and the absence of other effects that would change this distribution of particles, results in a power law in some spectral range between two frequencies that correspond which correspond to the characteristic frequencies of radiation of the electrons at the ends of that distribution. And so yes, in between that it's a power law. The index of the power law depends upon the index of the distribution of the electrons. Below that lowest frequency, you get this omega to the 1/3 tail from the lowest energy electrons, and at the highest, above the highest frequency corresponding to the highest energy electrons, you get an exponential cutoff. This exponential cutoff is usually not observed. There are other effects that typically end up happening, but sometimes this does become important. This is sometimes called, when we talk about synchrotron cooling, this omega 2 might be the highest energy electrons that remain in the system because higher energy electrons have cooled or disappeared. And in that case, this gets called, has a name, it is called the burn-off limit. And that's because those electrons have burnt off their energy into radiation. And so then you can have this exponential cutoff in the spectrum. So that concludes our discussion of synchrotron radiation in the context of a power law distribution of particles as from the concept of just the emission, right? So we are assuming that all of this radiation is visible to us. But as it turns out, in any given physical system, it may have some size such that there may be particles in front with similar distributions that actually start absorbing some of this radiation, and then that adds wrinkles onto this spectrum. In addition, it is possible that these electrons, because they are radiating, they're losing their energy, and that will change the distribution as well. This gamma will start marching inward because the highest energy electrons will lose their energy first, and so this omega 2 will start changing. You may have constant injection of particles, and that will add an initial break in the spectrum, and then you get more power laws, and that is going to be the focus of the next videos.